right, hi guys, welcome to our first video of the new year and of chapter 5. Today you are going to learn about intermolecular forces. You have just created the droplets on the penny, so here, just quickly, here is the penny, and you dropped water on the penny, and notice that a dome of water droplets were actually created. All right. And you're about to learn about why this happens. Why does the water stay on the penny and not fall off? All right. Okay, let's dive on in. So why does the water stay on the penny? It's because of these things called intermolecular forces. Well, first let's define what those are. Intermolecular forces are forces between elements and molecules. And they are the forces responsible for keeping elements in their phases, either being a solid, a liquid, or a gas, okay? The first force that you must know are the London dispersion forces. These occur in all molecules. Okay? They are the weakest all right, and they are temporary. And they are a temporary arrangement of positive and negative charges, which create a short light. Honestly, let's just say a short attraction. Which creates a short attraction between the molecules. All right. So for instance, I guess the best way to describe this is that the electrons will start to shift, even if they're being pulled one way or the other. They tend to shift, and this shifting creates this temporary arrangement. Awesome. And I want you to know that this occurs in all molecules, so please remember that, all right? Okay, that is London dispersion forces. So every molecule has these types of forces because elements, they don't always stay, electrons don't always stay in their place. They tend to shift. They tend to kind of move around a bit. Creating a more positive side. And a more negative side. and then it will shift again. And keep shifting, okay? Awesome. All right, the next one are the dipole-dipole forces, okay? These occur for polar molecules. Okay. So again, these occur for polar molecules. Okay. Polar molecules, again, is when there is a knot, when they do not share electrons equally. Okay, and this creates a dipole attraction. So for instance, if we had fluorine bonded to little tiny hydrogen, we would create this thing called a dipole. So I'm underlining dipole in red, and what I'm drawing in red is a dipole, okay? It's this dipole attraction between the positive and negatives. So dipole attraction between the positive and negative. So fluorine is more electronegative and therefore it wants the electrons, so it's going to pull strongly, creating that negative charge, okay? Where hydrogen is less electronegative, it doesn't want electrons, and therefore it's going to be pulling not strong. Actually, not strong, we'll just say weak pull. That's even easier. Okay, which creates that positive charge. And because hydrogen is positively charged and fluorine is negatively charged, it creates this dipole attraction, and other hydrogens and fluorine molecules will become attracted to each other, and another hydrogen fluorine molecule will become attracted to the next one. Okay? All right. So just a few more notes about dipole-dipoles, that this partial positive and negative dipole moment attracts other molecules with other dipole moments. So again, it just attracts other molecules that also have dipole moments. So again, this hydrogen and fluorine created a dipole, and this hydrogen and fluorine create a dipole. And so the positive is attracted to the negative, and the negative is attracted to the positive, and that's how we can get a bunch of these hydrogen and fluorine molecules attracted to each other to make a large substance. Okay? All right. And now we're on to just our last one. So the last one is hydrogen bonding. This also occurs with polar molecules. Okay. Hydrogen bonding occurs when hydrogen is bonded to nitrogen, oxygen, and fluorine. It only happens when it's bonded to those three. Nash is growling. My apologies. Okay. When hydrogen is bonded to one of these three molecules, it creates a polar bond. All right, so polar bond is created. This polar bond is very strong. So this, in fact, is the strongest force. Okay, and so if we were to look at hydrogen bonded to oxygen, it creates that dipole. If we were to look at hydrogen bonded to nitrogen, that dipole is also created. And if we were to look at hydrogen bonded to fluorine, that dipole is also created. And that dipole is very strong, okay? The electronegativity values are very large, or the difference, I guess. All right, and so let's think about water. So this is what I find to be really interesting. So water is H2O. We have our oxygen bonded to our hydrogens. Oxygen is going to be pulling more strongly on the electrons because it is more electronegative. So oxygen is going to be pulling on the electrons from both the hydrogens. So that means oxygen is going to be really negative, okay? And the hydrogens are both going to be very positive. So let's put water into a glass and put multiple H2O molecules in here. So we have okay. So our oxygens are positive. Our oxygens are negative. And our hydrogens are positive. The positives and the negatives are going to attract each other. And this is why water is very strong as a liquid and able to build on top of that penny and not fall off. It builds because of the hydrogen bonding. And that hydrogen bonding creates those very strong dipoles, those very strong positive and negative charges, which then attract other water molecules to each other. All right? So this is why the water can build / stay on top of the penny. Okay. From here on out, for the rest of class, you are going to work on a few simulations that show the intermolecular workings of these forces, and with the penny again, just through simulation. These notes will be collected, and then we're going to do your exit ticket and call it a day. All right, good work, guys. Have a nice night. Oh, not night. I'm going to bed. Oh my God. Have a good rest of class. All right. Bye, guys.